Hello, everyone. So we have finally reached what is, in most people's opinions, the hardest topic in calculus, which is related rates. Most professors would say this to you. Most college students would say this to you. And honestly, once you get through this chapter or this section, you pretty much will be able to get through anything. So essentially, what we're going to be seeing with this set of problems, you're going to see word problems. Everyone's nightmare, word problems and calculus together. And really, there's a set of guidelines that I went ahead and wrote for you that a lot of people recommend, but I mean, these guidelines, they're a recommendation. It doesn't necessarily mean that this is going to work for everything. There's always going to be like maybe an extra step for certain problems, but this should at least give you some kind of starting point. So the first thing you guys should do whenever you read these word problems is draw a picture of what's going on and label your quantities. You're going to see me do this for every single problem, except for example one. This one doesn't really require a picture, but a lot of these scenarios, if you visually see what's going on, you should be you'll be better off getting ready to answer the question. Then, and this is something that I did in engineering school all the time, write your given values from the problem and write your find. So if you start identifying what it is that you're given and then what it is that you're trying to solve for, it'll help you stay organized, right? And that's the best thing I can recommend for this chapter. Stay as organized as possible. The next thing is write an equation that relates to variables, all right? So for those of you who struggled with geometry, for those of you who struggled with trigonometry, it's going to come back and bite you in the butt, because essentially, a lot of these things, you're going to be talking about spheres, maybe some cones and balloons being filled up for whatever, for anything, and you need to know what those formulas are. Sometimes they embed the formula in the problem, sometimes they don't. And most of these I went ahead and did that. Well, not all of these, but yeah, you need to find an equation that relates all of the different variables. Once you see your picture, once you see the image of what's going on, you're going to create the equation. The fourth thing, and this is extremely important, I know with implicit differentiation, we're used to saying, if we differentiate 2y, for example, then we would, the derivative of that would be 2y times dy over dx, right? So in other words, we're taking the derivative of all these things with respect to x. But this time, we're going to be differentiating with respect to time. So for example, if you see 2x plus y squared, for example, and I ask you to differentiate this, you're going to take the derivative of every variable, but you're going to divide it, but you're going to take it with respect to time. So for example, if I took the derivative of 2x, well, that'll just be 2, but we're going to multiply it by dx over dt, t being for time. Then derivative of y squared is going to be 2y, right? But then we're going to do times dy over this time dt. So every time you see a variable in an equation, you're going to differentiate that variable with respect to time. Very important here. All right, because these are all related rates, and it's going to involve some unit of time. The fifth thing you need to do is substitute the known quantities and rates and solve. So once you end up doing all of your differentiation and finding everything with respect to time, you're just going to have, this is why it's important to have your list of given values. So with your list of given values, you're going to plug that into the equation or what you just differentiated, and you're going to go ahead and solve for it. So okay, I'm gonna move on, and I'm just gonna say let's get through it. I have 6 problems for us to practice, and I'm just warning you right now, this video is going to be long. Well, you're probably seeing that if you clicked on the video. So, for example 1, it says suppose x and y are both differentiable functions of t and are related by the equation y equals x squared minus 3x. Find dy dt when x is equal to 3, given that dx over dt is equal to 2 when x equals 3. So this is as basic as it's going to get, and I wanted to just introduce this to you to show you the concept of differentiating with respect to time. So if I have my given values, well, what I'm given is the formula, or the equation. Sorry about that, I got interrupted. But, so yeah, what we're given here is we're given y is equal to x squared minus 3x, okay? So we have our that given, and then we're also given that dx over dt is equal to 2. And pretty much we're also given that x is equal to 3. So that's what we're given. But we need to find, and it says it in the problem, find dy over dt. All right? So I'm going to go ahead and, so that's our given, that's our find, and I'm going to go ahead and write the solution right here. So as far as the solution is concerned, we need to get our original equation, y equals x squared minus 3x, and then differentiate it. So when we take the derivative of y, that's 1 dy over dt. Again, every time you take the derivative variable, you're multiplying it by dy with respect to time, is equal to x squared is going to be 2x dx over dt, minus derivative of negative 3x is 3 dx over dt. Okay? So now that you went ahead and differentiated, this is the part where we're just going to substitute the known quantities and rates and solve. So this is obviously what we're trying to find, and it's just multiplied by 1. So we know that dy over dt is equal to 2, x is 3, dx over dt is 2, minus 3 times 2, and then we get 12 minus 6 is 6. All right, and that's what dy over dt is equal to. All right, so that's as basic as it's going to get. So let's go ahead and actually apply this to some scenarios. So for example 2, it says a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So, all right, I'm going to see if I can draw this as best as I can, but essentially it's saying that you have like some concentric circles and it's forming ripples. So a little pebble drops in the middle and it just kind of forms like little concentric circles like that. Okay, and then we have like a radius there and all of that. So our given values, all right, well, let's see what they told us. They told us that the radius of the outer ripple is increasing. So, and this is important, when you're seeing the word increasing, you have to think positive. If it said decreasing or it depends on the direction, then you got to make sure that you would use a negative value. But here it's increasing, so we know we have a positive value at a constant rate of 1 foot per second. So we know that the rate of the radius, right? So the radius of the outer circle is at a constant rate. So the rate of the radius with respect to time is equal to 1. And I'll just write the units here, 1 foot per second. All right. They told us that they want us to find, to figure out the rate of the area at a radius of 4. So we're going to use r equals 4 in our formula. And well, this is where we kind of have to start using our intuition. What type of figure are we working with here? Well, we're working with a circle in the area. So hopefully we should remember that the area of a circle is pi r squared. I mean, if you guys need it, maybe I can try to come up with a list of geometric formulas, but I mean, you know, calculus comes after geometry, so the assumption is you know what these formulas are. So then what they want us to find, so the question is asking, at what rate is the total area of the, so they want to know what is the rate, basically the rate of the area. So that is dA over dt. Okay, so this is what we're trying to find. All right, so now when we go ahead and write out our solution, this one is pretty straightforward too. We have A is equal to pi r squared. So we got to differentiate our formula. So when I differentiate A, the derivative of A is just going to be 1 times dA over dt is equal to, that's just a constant, so I'm going to leave the constant there. And then we would bring the 2 to the front, or bring the 2 and multiply because it's a power rule. So times 2r. And we took the derivative of r, so it's going to be dr over dt. So again, every time you see a variable, you have to multiply with the rate of that variable over time, okay? Or differentiate it with respect to time. So now that we have this, it's just a matter of plugging in our given values or what we have, right? So we're trying to find this, so we can just leave that as that, over dt is equal to pi times 2 times a radius of 4, and dr dt is 1. So then we're going to end up with 8 pi, right? And the units for area, well, that's going to be, you know, if we're dealing with feet, area is feet squared. But since we're dealing with respect to time, it's over per second. So feet squared per second. And that's the final answer there. Okay. So another pretty straightforward example. Let's do this one, example number 3 is what I meant to say. I'll fix that in the notes. Example number 3, a police car approaching a right-angled intersection from the north is chasing a speeding car that has turned the corner. So here's the police car, and then here's a speeding car that turned the corner this way. And is now moving straight east. I gotta remember my car. North, and then we. Okay, so it's going this way. So the speeding car is moving in this direction, and the police car is obviously chasing it, so it's going down. I always like to draw my arrows to show my direction because that you'll see why in a second. So it says when the police car is 0.6 miles north of the intersection, and the car is 0.8 miles to the east, the police determine with a radar gun that the distance between them and the car is increasing at 20 miles per hour. If the police car is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? So, all right, so first of all, we have a right triangle here. I think you can see that right there. And I had to decide what variables I'm going to use. Maybe some of you would want to use A, B, and C. I'm just going to go ahead and use X, Y, and Z. So I have X, I have Y, and I have Z. Okay. All right. So what else? What other information do we have here? So I know that the police car is points. So at the moment that they're interested in determining this, right? Because at the instantaneous, like we're going to find the instantaneous rate of change of something. When the police car is 0.6 miles north of the intersection, so that means that this distance right here is 0.6. Okay, and the car at this moment is at a. Okay, sorry, I got interrupted again. So hold on. So I don't even know what I was saying. So we know that the police car is at a distance of 0.6 and the speeding car is at a distance of 0.8. So we're going to go ahead and see. And really, if this is a right triangle, we can figure out what this hypotenuse is, right? Because we know that for a right triangle, it's going to be like Pythagorean theorem. We have x squared plus y squared equals z squared, right? So I can go ahead and just do 0.6 squared plus 0.8 squared. And then is equal to z squared. So I know that z is equal to, when I do all of that math, 0.36 plus 0.64 square root is 1. Right? So I know that that distance currently is 1. So I'm just going to go ahead and put that in there right now. So what other information do we have that the problem is given us? So, okay, so they say that the police car... Oh, that so with this radar gun, the officers realize calculating or seeing that the distance between them is increasing at a rate of 20. So this distance is increasing at a rate of 20 miles per hour. So that's how we say it. dz, so the rate of this distance is equal to, and it says increasing, so I'm going to use positive 20. Okay. And then what else are they saying? They're saying that the police car is moving at 60 miles per hour at the instant of measurement. Now, this is why I think it's important to draw your arrows. If the police car is moving at 60 miles per hour, that's dy over dt is equal to 60. But the one thing, and this is the thing that I know is going to screw up a lot of people if you don't pay attention to the direction that things are going. If you remember from the previous section, we were talking about position, velocity, and acceleration. The direction of which the velocity of the object is going is extremely important. If the police car is moving south, then that means you're going to have negative 60 right there. All right. So please try not to get that messed up. So I'm going to go ahead and write my given values. I'll just write it over here, down here. It doesn't matter where it is. So I know that x is equal to 0.8. I know that y is equal to 0.6. I know that dx, no, not dx. I know that dy over dt is equal to negative 60. I also know that dz over dt is equal to 20. I guess I found out that z was equal to 1. And what I need to find is dx over dt, because what they ultimately want to know is what is the speed of this car. So dx over dt, we have no idea what that is. All right. So, all right, now let's just go ahead and get started with the solution. So the solution is, first of all, the equation that relates all of these variables is this one. We have x squared plus y squared is equal to z squared. So what I'm going to go ahead and do is differentiate this. So when I take the derivative, I have 2x and then times dx over dt plus 2y times dy over dt is equal to 2z times dz over dt. All right. So I can divide it. I mean, really, I can divide everything by 2 and then cancel it to 2s. I'll just leave it there, whatever. So now I just go ahead and plug in what I need, and this is the unknown value that I need to solve for. So I have 2 times x, which was 0.8 dx over dt, plus 2 times y, which is 0.6, dy over dt is times negative 60, is equal to, and then I have 2z dz over dt, so 2, and then z is 1. dz over dt is 20. And that's pretty much almost everything. So this becomes 1.6 dx over dt plus, where's my calculator? I'll just use this baby one. Let's see. So I have 2 times 0.6 times 60. So that's going to be negative 72, sorry, is equal to 40. Now it's just basic algebra for here. I'm going to add, so I'm going to do 40 plus 72. So 72 plus 40 is 112 divided by 1.6. I get 70. So dx over dt is equal to 70. And let's go ahead and use the units. Obviously, cars are accelerating or are going at a velocity of 70 miles per hour. And that's that problem. All right. So still not the hardest type of problem that that you'll see, but it's a little bit more involved. You'll notice that you were given a bunch of values, but you had to take the extra step and solve for z. And some people forget to do that. So that's why I wanted to include this problem in the notes. All right. Now for probably my least favorite problem in this, and out of all these examples, we're going to do example 4. All right, so this one says a rocket lifts off at the Kennedy Space Center in Florida. A camera is placed 2,000 feet away from the launch pad to film the rocket's ascent, I don't know how to pronounce that. The height of the rocket can be found using S of t is equal to 50t squared, where S is feet and t is seconds. Find the rate of change in the angle of elevation. Find the rate of change in the angle of elevation of the camera at 10 seconds after liftoff. And I wrote that for some reason. Give me a second. Sorry about that. I went ahead and fixed the worksheet. So I'll make sure to fix that for you guys before I post it on Canvas. So I don't even know where I left off. So, okay, so they said that we have a camera placed 2,000 feet away. So I'm going to try my best to draw this picture. So there's going to be like a camera here, a rocket going upward, right? And or the rocket is going upward, and I mean, this is going to be like a horizontal distance, and then the camera is going to be looking up at the rocket this whole time. Okay, so we're dealing with pretty much another right triangle here, but I'll tell you right now, or warn you right now, this one is not nearly as simple as the other one. So they say that x is equal to 2,000. Okay, because you know, obviously if the camera is here, it's 2,000 feet away from where the rocket was launched. And here's the thing, what you'll notice here, and if we want to figure out what dx over dt is, right, this is pretty much the fixed position, right? It's not like they're moving the camera this way or moving the camera that way or up or down or anything like that. It's in the same position, so this x is always going to be the same. So what most people, you know, fail to understand is that the rate of change for this is just going to be 0. All right, that's going to help us eliminate a lot of variables when we actually work out the derivative. So we know that the derivative of x with respect to time is going to be 0. So now as far as the height of this, all right, so the height, first of all, they want to know at 10 seconds, all right? So I'm going to go ahead and do a little bit of math here, and I'm going to say, okay, well, s of 10 seconds, that the moment that we're interested in calculating the rate of the angle, is going to be 50 times t squared is 100. So it's going to be 5,000 feet. All right, so I'm just going to go ahead and say here that s is equal to, I mean, you could use y if you want, just try to not mess up with your variable. So s is 5,000, okay? And you know what? I might as well find what the rate of s is too. So I'm going to go ahead and just do ds over dt is equal to, well, I know that the derivative is 2 times 50, so that's 100t. And I'm just going to go ahead and plug in 10 seconds and find out what the rate of change of s is at that moment of 10 seconds. So if I put 10 in here, then that's going to be basically 1,000 feet per second, right? So I'm just going to put ds over dt is equal to 1,000. okay? All right, so what else are we pretty much given? Oh, sorry. So what else are we pretty much given? I should have written given here. So we're given that, Another thing we can pretty much solve for here is, I mean, if we have a right triangle, I can figure out what that hypotenuse is, right? So I'm gonna go ahead and figure out what the hypotenuse is. So z is equal to, I know it's z squared, but I'm just gonna go ahead and do just less steps. So z is equal to this squared plus that squared, square rooted. So 2,000 squared plus 5,000 squared. That's 4,000, 25,000. If I add them, that's gonna be equal to the square root of 29 million. No, sorry, 4 million and 25 million is 29 million. All right, so now we're dealing with some ugly numbers here. So z is equal to square root of 29 million. Okay, now we don't really have, and they don't give us any information about, do they? No, we don't have any information about the rate of this, so well, I'm just going to leave that like that. But what they are interested in finding is the angle of elevation. So the angle of elevation is this right here, right? Because if you're elevating like that, then the angle of elevation is that. So, all right, so let's go ahead and see what we have. So first of all, if we have an angle of elevation and we had a y value and an x value, you know, if you think about like SOHCAHTOA, for example, you know, some old hippie caught a hooker tripping on acid. All right. So if you think about SOHCAHTOA, we have the opposite and adjacent, and I would much rather deal with like 5,000 and 2,000. You could probably do something with cosine, but I already worked this problem ahead of time. And most of the time, whenever you have an angle of elevation, you're going to be using tangent anyway. So I'm just going to use tangent for right now. So we have our given value. What we're trying to find is what is the rate of the angle of elevation. So we're trying to find d theta over dt. All right, so let's go ahead and just work out our solution. So again, sometimes it's going to take a little bit of time to, like, you know, draw your diagram, figure out everything you have. But I mean, if you're organized like this, then the solution is going to be very straightforward. So the solution, well, the equation that I can use that relates all of these variables, and the one that you're going to use often with an angle theta, is going to be tangent of theta is equal to opposite over adjacent. So it's going to be opposite of, the opposite is s, and then adjacent is x. I'm going to leave the variable. Even though I know what s and x are, we have to differentiate this, and we have to leave them as variables. So now we go ahead and differentiate this. So I have tangent of theta, derivative tangent of theta is secant squared of theta. That's equal to the bottom times the derivative of top, which is 1 ds over dt, minus the top times the derivative of the bottom, which is dx over dt, over, if you haven't figured out by now, I'm recording this during first period. Anyway, so yeah, so minus s times dx over dt divided by x squared. So right off the bat, I can make this a lot simpler. I already know that dx over dt, when we realized here, this is equal to 0. So really what we're working with is just x ds over dt divided by x squared. And now if I'm only dealing with one term on the top and one term on the bottom, I can simplify this. I have 1x down here and 2x's down there. Cancel that, cancel one of those. And so I'm just going to go ahead and rewrite it. I'm going to say secant squared of theta is equal to, oh, whoops, I forgot. So tangent theta secant squared of theta times d theta over dt. My bad. So d theta over dt. Sorry, because theta is a variable. So this is equal to ds over dt divided by x. All right. And so now we can go ahead and plug in some values that we have. So if this is what we're trying to solve, I'm going to go ahead and move the secant squared theta to the other side. So I have, or what I'm going to end up with, so if I divide both sides by secant squared theta, I'm going to end up with over here, or like multiplying both sides by 1 over secant squared theta, right? Well, if you know that secant of theta is 1 over cosine, this is pretty much the same thing as just cosine squared of theta. So if I go ahead and work this out, I can rearrange this to where I have d theta over dt is equal to cosine squared of theta, and then times, obviously, ds over dt over x. So now I'm going to go ahead and start plugging in my known values. I have d theta over dt is equal to, so cosine of theta. Now I'm going to look at cosine of theta. I'm going to look at this problem, and I'm going to look at theta, and I say, well, cosine from SOHCAHTOA is adjacent over hypotenuse. So I'm going to rewrite that as adjacent of 2,000 over the hypotenuse of the square root of 29 million. And then all of this is going to be squared. ds over dt we found out was 1,000, so it's going to be 1,000 over x of 2,000. All right, so we're almost there. So now this is going to be equal to, let me write this out, I'm going to do 4 million, because we have to square the top and square the bottom, so 2,000 squared is 4 million. And then that's going to cancel the square root, so we have 29 million. And then this reduces down to pretty much 1/2. So really the million and million, all those zeros are going to cancel out with all of these zeros. And then the 2 cancels out with that 4 to become 2. So finally, d theta over dt is equal to 2 over 29 radians per second. So yeah, not a lot of fun. You had to tie back a lot of different things, but again, the only way you're going to get good with these style of problems is if you actually practice as much as possible. All right, I'm going to pause. I'm going to take a little break from the video because the bell's about to ring for first period, and then I'll just continue recording for third period. See you guys later. All right, so the next example is actually involves the use of a cone. And I was nice enough to go ahead and write out the formula for you right here. So it says that water runs into a conical tank at a rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? So right now, this right here is representing like the height of the water at the moment. So we know that this height, as they say, is about 6 feet. And they say that the height of the whole cone is, just grab my little fancy bracket here, is 10 feet, and that the radius from the base of the cone is 5 feet right there. Okay, so that gives us some information. And now they also say that the water runs into the conical tank at a rate of 9 feet cubed. So first of all, the fact that that's saying feet cubed, that should kind of indicate to you that this is a related to volume, and it's a rate of the volume. So as far as our given information is concerned, we're given that the rate of the volume is equal to 9. Right? I could write the units, but I don't really feel like it right now. And they also want to know what is at the moment that it's 6, or at a height of 6. They want you to find how fast is the water level rising when the water is 6 feet deep. So, they want to know what is the rate of the height as it's rising. So as it's rising, that's rate of the height. So dH over dt. Okay? And it looks like that's all the information that they've given us. So so I was nice enough to provide you with the formula for the volume of a cone. I don't know if that's always going to necessarily be the case, but, we'll see. So we have over here that, so as far as our solution is concerned, we have over here that the volume of a cone is equal to 1/3 pi r squared times h. Now, typically, and what we've been doing up until now is we've been differentiating the formula function that we have. Now, don't write this part down. I'm going to go ahead and do that here on like a separate sheet of paper, but let's kind of see what happens when we do that. If we differentiated this, derivative of v is dv over dt is equal to, and then we can just do, we're going to have like the product of two numbers, right? So we're going to do the product rule. So the first, I'll just include the constants with the first one. So the first times the derivative of the second plus the second times the derivative of the first. So that'll be bring the 2 to the front. So that's 2/3 pi r. And then we took the derivative of r, so it's going to be dr over dt. All right. So sure, this is what our derivative, but there's a problem here, right? I mean, we can probably figure out what r is because we do have similar triangles here and figure out what the r is at that instant. But the issue here is that if you read throughout the whole problem, they don't say anything about what is the rate of the radius with respect to time. You know, they want you to find the dH over dt, or the rate of the height with respect to time. They give you the rate of the volume with respect to time. But this, we have no idea what that is, and we just don't have enough information to actually solve that. So this is one of those problems where you kind of have to, you know, manipulate what you have and only take the derivative of things that, you know, you can work with. So the suggestion here is to pretty much eliminate r from this whole thing. So now we have to go back to this figure, and again, I'm telling you, this is probably one of the highest level styles of problem you'll see in this class. So we're gonna have to look at our original figure and say, okay, well, here's the thing. If you notice here, I do kind of have similar triangles, and I don't know if you guys remember from geometry, I really hope you do, but if you have similar triangles, like, you know, a triangle within a triangle, you can pretty much create a proportion from this. So they said that the height was, that the whole thing was 10. This height, let's just label it as h. This radius is r. And this, the total radius of the whole cone is 5, right? So really what we can do is we can create a proportion based off of similar triangles. So we'll do maybe like the radius over this height is going to be proportional or equal to the radius over this height, right? And so if I multiplied height to both sides, I'll just go ahead and say that the radius is equal to, this reduces down to 1/2 times h is that. Okay, so I know that the radius is equal to 1/2 times the height. So if I know that this is equal to that, I can just go ahead and substitute 1/2 h inside of r. So I know that volume is also equal to 1/3 pi times 1/2 h squared times h, right? So I'm just gonna go ahead and rewrite my formula. So my volume is equal to, let's see, 1/2 squared will be 1/4. 1/4 times 1/3 is 1/12. So that took care of the constants. Then I have pi there, I can't forget that. And then this will become h squared, and h squared times h is h cubed. Okay? So I know that the volume, at least for this specific cone, is going to be 1/12 times pi h cubed. So now, if I actually went ahead and took the derivative of this, I'll end up with dv over dt is equal to, if I bring the power of 3 to the front, because this is all just a constant, so the constant times the power, 3 over 12 is 1/4 pi, subtract 1 from the power, and then we took the derivative of h, so we're going to multiply it by dh over dt. Okay, now this is helpful. Now we have variables that we can actually plug into this, and then finally solve for this one, for the dh over dt. So we know that dv over dt is equal to 9. We have 1/4 pi h squared, so I'll just write it out, 6 squared, and then this is what we're trying to figure out. Okay, so this becomes 36. 36 divided by 4 is 9 pi dh over dt. So then if I divided both sides by 9 pi, I get dh over dt is equal to 9 over 9 pi reduces down to 1 over pi, right? And if it's the rate of the height, the unit is just so the height unit is just feet per, and then time, what are we, oh, we're dealing with minutes, so feet per minute. And that's our answer. All right. So again, it's not that difficult. If I told you in advance, you know, make sure you substitute r, but the problem is they're not going to tell you that when you actually have a problem. Sometimes you're going to have to derive what you have and realize, man, I just don't have all of the variables that I need. So you're going to have to do some kind of manipulation and see what else you can create from your figure and your original data, and you know, manipulate it so that it's something that you can work with. Last example. All right. I know this video is long, but we're getting through it. So we're talking about a sliding ladder here. So it says the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. When the top of the ladder is 7 feet from the ground, what is the rate of the distance between the bottom of the ladder and the wall? Okay, so I know we have a wall. There's obviously going to be a ground, and there's a ladder that's kind of leaning up on it. Okay, so that's about the best picture I can draw for that. So it says here that the 25, so it's a 25-foot ladder. So I'll just use my X, Y, and Z like before. So Z is equal to 25. Now, I mean, the ladder isn't necessarily, it's probably not one of those ladders that, like, you know, changes distance. I know there's some ladders that exist that can, you know, change height, change its length, but we're just going to assume that this is one of those ladders that stays at 25 the whole time. So in that case, if it's going to stay the same, it's going to constantly be 25. Our dz over dt is equal to 0. All right. And it says that the top of the ladder, so this top of the ladder is sliding down. So I'm going to draw my arrows to show the indication. And I mean, you can just kind of, like, you know, use your imagination and see that if this is sliding down, then obviously this point is going in that direction. Kind of similar to like the cop and the driver going away from it. So, all right, so what other information do we have? So 25-foot ladder, constant. So, okay, so it's sliding down at a constant rate of 3 feet per minute. So if it's going down, the down rate is dy over dt is equal to, and it's, so if it's going down at 3 feet, it's -3. There's that negative sign that I feel like a lot of you are probably going to screw up, and hopefully you don't. And then they say when the top of the ladder is 7 feet from the ground. So the top of the ladder at this moment that we're trying to calculate is 7 feet from the ground. What is the rate of change of the distance between the bottom of the ladder and the wall? So they want to know what is the rate of change of dx over dt. Okay, so looks like here we have almost everything. We have y, we have z, we have the rates of the 3 of them, but we're missing x. So luckily, with this being a right triangle, we can just go ahead and use Pythagorean theorem. So I know that it's 7 squared plus x squared is equal to 25 squared. It's 49 equal to 625. Pretty sure it's 24. Oh yeah, it's one of my special triangles. So 7, 24, 25, but whatever. I'll just do all the math. So this is x equals to 24. Okay. So now it's just a matter of using whatever formula we have. So what we're given y is equal to 7, and at the same time dy over dt is equal to -3. We're given that z is equal to 25, and the z over dt is equal to 0. We're given that x is equal to 24. Well, we weren't given that, but we figured it out. And what we're trying to find is dx over dt. So now as far as my solution, I'm going to go ahead and write out my formula. I have x squared plus y squared equals z squared. I derived this. I have 2x dx over dt plus 2y times dy over dt is equal to 2z times dz over dt, right? I can go ahead and just kind of make this a little bit short. If I know that dz over dt is equal to 0, that cancels out and becomes 0. And then, yeah, we can just plug in everything else that we know. So 2 times x, that's 2 times 24. This is what we're trying to find, so I'm going to leave it like that. Plus 2 times y, which is 7, times dy over dt is -3. And then that's all equal to 0. So this becomes 48 dx over dt. This becomes -21 times 2 is -42. So I'll add that to the other side and make it equal to 42. And then dx over dt is equal to 42 over 48. Both of those are divisible by 6, so it's just becomes 7 over 8. My units for x is, that's a distance, and it's feet, so feet per, and then what is the time units here? Minute, so feet per minute. All right. So hopefully that gives you guys enough practice, enough explanation of how to come, approach a lot of these related rates problems. Like I said, this is easily one of the most difficult topics that that you'll see, and the one that most calculus students struggle with. But just give it enough practice. I'm going to give you guys the weekend to do as many problems as you can on this, and I'll probably make the problems that due on Sunday or maybe Monday if you guys need it. So I'll let you guys go. Hopefully this was helpful, and good luck.